In the last lecture, we left off with the exact value chart, and we were talking about the unit circle and the fact that the sine of, let's say, 30 degrees is the same as the sine of all of the other angles in the unit circle that have a reference angle of 30 degrees. So I'd like to start with a brief retrospective. So what that means is I'm going to go back to that exact value chart for a few minutes, and then we're going to go even further back to the very first lecture where we talked about how to find all 6 trigonometric functions given a single trigonometric function. Okay, so we're going to briefly revisit that, and then we're going to look at the graphs of all of the trigonometric functions. So let's start with that exact value chart. So if we take a look at it, this is what it was, okay? And we said these are the angles at the top. These are the angles in radians. You should be very familiar with that. Okay, so we haven't done a tremendous amount of work with radians, but when we get to trigonometric equations, which is coming up soon, you're going to be working with radians a lot more than you will be working with degrees. So you should become familiar with that. But we said, okay, so we have 0 degrees, 30, 45, 60, and 90. These are angles that we know the exact values of, meaning we know the exact value of the sine, the cosine, and the tangent. Okay, note that we would also know the exact value of the cosecant, the secant, and the cotangent because they're just the reciprocals. So for example, if the cosine of 0 is 1, the secant of 0 is 1 because the reciprocal of 1 is 1. If the cosine of 60 is 1/2, the secant of 60 is 2 because the reciprocal of 1/2 is 2. If the cosine of 90 is 0, then the reciprocal, the secant of 90 is undefined because 1/0 is undefined. If the cosine of 30 is square root of 3/2, then the secant of 30 is 2 over the square root of 3, or 2 square root of 3/3 if we rationalize the denominator. Okay, so you can see that we could figure out all 6 of the trig functions. Okay, let's go back though and look at other angles that have the same reference angle. Okay, so we're looking at the sines, cosines, and tangents with the same reference angle and we discussed reference angles in the last lecture as those in the exact value chart. So when we introduced the exact value chart, we were saying, well, once we know the sines, the cosines, and the tangents of reference angles, then we also know the sines and the cosines and the tangents of any angle that has the same reference angle. So let's take an example. Let's take 30 degrees. And we won't do this for all of them, but we'll do it for most of them. So if we have 30 degrees, okay, then based on the exact value chart, we know that the sine of 30 is 0. Sorry, sine of 30, here's 30 degrees. Sine of 30 is 1/2. Cosine of 30 is square root of 3/2, and the tangent of 30 is square root of 3/3. So let's just write that down. Sine of 30 is 1/2. Cosine of 30 is square root of 3/2. And the tangent of 30 is 1 over the square root of 3, but if we rationalize the denominator, that gives us square root of 3/3. Okay, now what does this mean? There are other angles that have a reference angle of 30 degrees. So for example, in quadrant 2, if this is 30, then the angle is 180 minus 30. This angle here is 150 degrees. Okay, 150 degrees has a reference angle of 30 degrees. So what does this mean? Well, in quadrant 2, so we'll go back a little further. In quadrant 2, the sine is positive, the cosine is negative, and the tangent is negative. So what does this mean? This means that the sine of 150 degrees is going to equal the sine of 30 degrees. They're the same in both quadrants. The sine is positive in both quadrants. So the sine of 150 is 1/2. Now the cosine of 150, well, in quadrant 2, remember in quadrant 1, everything is positive. Okay? In quadrant 2, the cosine is negative. So this would be the negative cosine of 30 degrees. Or negative square root of 3 over 2. And the tangent is also negative in quadrant 2. So the tangent of 150 is the negative tangent of 30 degrees, or negative square root of 3 over 3. Now we could look at the same thing in quadrant 3. So in quadrant 3, the angle, if this is 30 degrees, okay, the angle that's equivalent to 30 degrees, which would come all the way around like this, that angle is 210 degrees because we're going 180 degrees around plus an extra 30. Okay, so what does this mean? Well, the sine of 210 degrees in quadrant 3, the sine is negative. So the sine of 210 degrees is negative sine of 30. Or negative 1/2. So we know that the sine is the same as the sine of 30. We just have to figure out, is it going to be a positive number or a negative number? So in quadrant 3, sine is negative, so it's going to be negative 1/2. In quadrant 3, cosine is negative. So it's going to be the negative of the cosine of 30, or negative square root of 3 over 2. And the tangent of 210 degrees in quadrant 3 is positive. So it would be the same as the tangent of 30 degrees. So tangent of 30 is square root of 3 over 3. Okay, and then we have the same angle in quadrant 4. We'll do that one in green. We have a reference angle of 30 degrees. So we have 4 angles that all have the same reference angle. Okay. This one, if we go all the way around, this one has an angle of 330 degrees, right? It's just 30 degrees short of 360. So it's 330 degrees. So let's go through it for 330 degrees as well. So the sine of 330 degrees is negative the sine of 30. Sine is negative in quadrant 4. So this would be negative 1/2. Cosine in quadrant 4 is positive. So the cosine of 330 degrees is equivalent to the cosine of 30, or square root of 3 over 2. And the tangent of 330 degrees, well, that's going to be the tangent of 30, the negative tangent of 30, because tangent is negative in quadrant 4. Okay, so again, notice it's all the same numbers. It's just that sometimes it's positive, sometimes it's negative, depending upon what quadrant we are in and what trig function we're looking at. Okay, now we're not going to do this for 60 and 45, but we'll do it for 1 in each of them. Okay, so we won't do it for all 4 quadrants. Okay, so this we did for all 4 quadrants. In quadrant 1, it's 30 degrees. In quadrant 2, it's 150. In quadrant 3, it's 210. And in quadrant 4, it's 330. All of these have a reference angle of 30 degrees. But let's say that we wanted to figure out the sine of 135 degrees. Okay, well, the first thing that we need to do is we need to figure out the reference angle. So 135 is between 90 and 180. So to figure out the reference angle, we're in quadrant 2. We do 180 minus 135. And we get a reference angle of 45 degrees. Okay, so now we know that the sine of 135 degrees is equal to the sine of 45 degrees. We just need to figure out, is it positive or is it negative? Well, 135 degrees is in quadrant 2, and in quadrant 2, the sine is positive. So this is the sine of 45, which is square root of 2 over, that does not look like a 2, square root of 2 over 2. Okay, if we go back to our exact value chart, you can see the sine of 45 is square root of 2 over 2. Okay, let's say that we wanted to find the tangent of 300 degrees. Once again, we have to find our reference angle first. So 300 degrees is in quadrant 4. In quadrant 4, we take 360 and we subtract the angle. So we get 60 degrees. Okay, so this is telling us that the tangent of 300 degrees equals the tangent of 60 degrees. But in quadrant 4, tangent is negative. So it's the negative tangent of 60. And the tangent of 60 is square root of 3. So the tangent of 300 degrees is negative square root of 3. Let's do one more. Let's say that we want to know the cosine of 240 degrees. Okay, so once again, we want to find our reference angle first. So 240 is in quadrant 3. Okay, how do we know that? Because it's between 180 and 270. So in quadrant 3, we take the angle and we subtract 180 degrees. (240 minus 180 gives us 60 degrees. So we're saying that the cosine of 240 degrees is equal to the cosine of 60 degrees, but it's negative because in quadrant 3, cosine is negative. So the cosine of 60 is 1/2. So that means that the cosine of 240 is negative 1/2. So we have a lot of angles that we could figure out. The reference angles that have, the angles that have a reference angle of 45 degrees are 135 degrees in quadrant 2. In quadrant 3, it's 225 degrees. In quadrant 4, it's 315 degrees. So we could find the sine, the cosine, and the tangent of all of those angles. For 60 degrees, sorry about that. For 60 degrees, the reference angle, the angle in quadrant 2 that has a reference angle of 60, is 120 degrees. In quadrant 3, it's 240 degrees. And in quadrant 4, it's 300 degrees. Okay, so we can find the sine, the cosine, and the tangent for all of those. And then for 30 degrees, you see it's 150, 210, and 330. Now for 0 and 90, okay, 0 and 90 are not considered reference angles because reference angles are acute angles, and these are not forming angles at all. It's just two lines. We can't call them acute angles. But for 0 and 90, we could figure out the sine, cosine, and tangent based upon what we know about the unit circle and the fact that the unit circle, our coordinates are 1, 0, 0, 1, -1, 0, and 0, -1. And if you remember, at each of those angles, we know that the sine is the y value and the cosine is the x value. And we're going to be using this to help us graph. So we're going to come back to that. But that means that we can figure out the sine and the cosine not just of 0 and 90, but also of 180 and 270, because we could just look at the coordinates over there. So we could figure out the exact values for sine, cosine, and tangent of a lot of different angles. Okay? For all of the other angles, we don't know the exact values. Okay? But if it says exact value, it means no decimals. Okay, so one other thing to look back on is in our first lecture, we said, okay, well, what if we know that the sine of an angle is 3/7? What is the cosine, the tangent, and the cotangent, the secant, the cosecant? We were asking about all of those things. So I want to take an example and add in what we know about these angles, okay? The fact that we're in the second quadrant, the third quadrant, and the fourth quadrant, and whether the sign is positive or negative, okay? So let's take an example. Let's say that we know if sine of theta is equal to 3/5 and it terminates in quadrant 4. So it's actually negative 3/5 because sine is negative in quadrant 4. Let's find, we won't find all of them. Let's find the cotangent of theta and the cosine of theta. So we don't have to find all of them. We'll just find those two. So our process here is the same, okay? Nothing is going to change. If you remember our process, we identified the opposite and the hypotenuse, okay? We identified that because sine is opposite over hypotenuse. So the 3 we found was the opposite side and the 5 was the hypotenuse side, okay? So opposite is 3, hypotenuse is 5. And we said, okay, we can find the adjacent using the Pythagorean theorem. So we need that third side. This should look very familiar to you because we've done it before. Okay, this came from the end of the first lecture. So O squared plus A squared is equal to H squared. This is the Pythagorean theorem. And we're just plugging in 3 squared plus A squared is equal to 5 squared. 9 plus A squared is equal to 25. And then A squared is equal to 16. So A is equal to 4 if we take the square root of both sides. Okay, so now we have all 3. Now we want to know the cotangent of theta. So cotangent is adjacent over opposite. These are things that you should know. You should memorize. These are definitions. There's no way around it. You have to memorize. okay? So cotangent is adjacent over opposite, but we're talking about quadrant 4, so we have to take into consideration, is cotangent positive or negative in quadrant 4? Well, if tangent is positive, then the cotangent is positive. If tangent is negative, then the cotangent is negative. So in quadrant 4, okay, sine is negative, cosine is positive. This means that tangent is negative, so cotangent is negative. So our cotangent is going to be negative 4 over 3. And we say it's negative, once again, this is negative because tangent is negative in quadrant 4. Okay. Whatever the trig function is, that's what the reciprocal trig function is. So if cosine were positive, then secant would be positive. If cosecant were negative, if sine were negative, cosecant would be negative. Okay. So we found the cotangent of theta. Let's find the cosine of theta. So cosine of theta is adjacent over hypotenuse. And we're at quadrant 4. In quadrant 4, cosine is positive. So we could just say that this is 4 over 5. It's positive because cosine is positive in quadrant 4. Okay, let's take another example. So notice that the fact that it's saying that theta terminates in quadrant 4, the only extra step that you have to consider beyond what we did in the past is your trig function positive or negative? If your trig function is negative in that quadrant, then you're going to make your answer negative. If the trig function is positive, you're going to make the trig function, you're going to make your answer positive. Okay, now this is one way to ask this question. I'm going to ask it in a slightly different way. Let's say if the cosine of theta is equal to 5 over 10 and tangent of theta, let's make this negative 5 over 10. And tangent of theta is greater than 0. Find cosecant of theta and cotangent of theta. Okay, so what's the difference? The difference is we're not told where theta is terminates directly, okay? It doesn't say and theta terminates in quadrant. This is saying, okay, our cosine is negative. So where is our cosine negative? Our cosine is negative. This tells us theta must be in quadrant 2 or quadrant 3. Okay. But this is saying that the tangent of theta is greater than 0. So this is narrowing it down to one quadrant. Okay. Tangent of theta is greater than 0. Where is that true? Out of quadrants 2 or quadrant 3. So from quadrant 2 or quadrant 3, the one where the tangent of theta is greater than 0 is in quadrant 3. So we would be looking only at quadrants 2 and quadrants 3 because our cosine is negative, okay? And which one gives us a positive tangent? Quadrant 3. Okay, so now we can find the cosecant and the cotangent. So we have to identify our opposite, our adjacent, and now our hypotenuse. We know that this is the adjacent and this is the hypotenuse. So O squared plus 5 squared is equal to 10 squared. Or O squared plus 25 is equal to 100. O squared is equal to 75. O is equal to the square root of 75, which is 5 root 3. Right? This is square root 25, square root 3. So O is equal to 5 root 3. You want to reduce it? You're going to have to reduce it anyway when you give your answers. Okay? So cosecant of theta. Well, cosecant is hypotenuse over opposite. And this is telling us it's 10 over 5 root 3. Okay. 10 over 5 root 3. Now we can reduce this, okay? You can reduce it because 5 goes into 10 twice. So this becomes 2 over the square root of 3. And we should mention before we even rationalize this denominator that the cosecant here is negative. In quadrant 3, okay, sine is positive, sine is negative, so cosecant is negative. So these have negative signs. And then we want to rationalize the denominator, so it becomes 2 root 3 over 3, okay? This is how we rationalized. So that's cosecant. Let's find cotangent. So cotangent is A over O. Our A is 5. Our O is 5 root 3. Okay? And cotangent is positive here. Okay? It's positive because tangent is positive. So whatever reciprocal, the reciprocal functions have the same sign. This we can abbreviate to 1 over root 3. The 5's cancel. And then once again, we can multiply by root 3 over root 3. And we get square root of 3 over 3. Okay, so I'm not going to do a lot of examples here because we've done it. What this piece does is it tells us which quadrant we terminate in. Okay, so it gives us this information. And again, knowing this information, the only thing extra that we have to do, other than what we did in the first lecture, is figure out if that trig function is positive or negative. And we're just going back to that idea of in quadrant 1, is sine, cosine, or tangent positive or negative? What about quadrant 2? Okay, and that has to do with the x and the y values. So speaking of that, let's go back to the unit circle because that's going to help us graph the different trig functions. So when it comes to graphing, you need to know how to get the graphs of sine and cosine, okay? Every other graph that we look at, because we're going to be looking at the graphs of the reciprocal functions and the graphs of the and the graphs of the inverse functions, the only thing that you have to be able to do is recognize the graph. So if I give you the graph, you should be able to say, oh, that's the graph of cosecant of theta, okay? So let's go back to the unit circle. We don't need it to look beautiful or perfect or anything. We just need the basic idea. So I'm going to just draw it here, okay? And in fact, I won't draw the whole unit circle. I won't draw the circle. We don't even need the circle. What we need are the angles and the sines and the cosines of those angles. And we're only going to look at the angles that are on the axes, okay? So we know that in the unit circle, we have the coordinate 1, 0. We have the coordinate 0, 1. We have the coordinate negative 1, 0. And we have the coordinate 0, negative 1. Okay, we also know something else. We know what angles these are. So we know the angles in degrees, okay? This is 0 degrees and 360 degrees. This is 90 degrees. This is 180 degrees. And this is 270 degrees. Now, why is this helpful? It's helpful. I don't know why this 0 isn't coming out. Okay. It's helpful because knowing that the sine is the x value, is the y value, and the cosine is the x value, we know that the sine of 0 is 0. The cosine of 0 is 1. The sine of 90 is 1. The cosine of 90 is 0. The sine of 180 is 0. The cosine of 180 is negative 1. Sine of 270 is negative 1. Cosine of 270 is 0. So we know the sines and the cosines of these angles, okay? But when we graph, we don't use degrees, okay? Imagine, so when we take the sine of an angle, the input is the angle, right? We're taking the sine of an angle. So the input, which is your x-axis, would be the angles. But here your angles go from 0 to 360. That is a lot of numbers on your x-axis. It's huge to go from 0 to 360, okay? Let's look at what this is in radians. So if we go back to what we know about radians, when you start the circle, you're at 0. And when you go all the way around, you're at 2 pi. Okay. Over here, you're at pi over 2. 180 degrees is pi. 270 degrees is 3 pi over 2. Well, these are much smaller numbers. 2 pi as a number is 6.28. Pi as a number, if you put it in decimal form, is approximately 3.14. These are much tinier numbers. We could deal with these numbers, okay? We're going now from 0 to 6.28 instead of from 0 to 360. That is much more reasonable. So what we do is we graph using radians. So I said before that one of the reasons why we learn radians is because the definition of a radian, okay, which remember it's the angle that's formed by an arc that's equal to the length of the radius, okay? Radians are a much smaller unit of measurement, okay? And because of that, it makes it much easier to graph. And remembering that our x values are the cosine of the angle and our y values are the sine of the angle, this is what's going to help us graph the different trig functions, okay? So let's go ahead and graph it. Let's start with sine. So on our x-axis go our inputs. Okay, and our inputs, this is going to be y equals the sine of theta, or the sine of x. Okay, we don't have to use theta. We're going to use x here because the reason why we're using x is because we're looking at the x-axis, okay, as opposed to putting theta on the x-axis. Okay, so our inputs are our angles. So we want to get every value of sine, and the way to get every value of sine is to do one full rotation around the circle. So we don't have to plot every single point. What we're going to do is plot the points where we already know what the sine and the cosine are. And it turns out that these 4 points are enough guidance to give us the sine and the sine of the angles, the graph, okay? So again, we're doing this in radians. So we're going to take the sine of 0. We're going to take the sine of pi over 2. We're going to take the sine of pi. We're going to take the sine of 3 pi over 2. And we're going to take the sine of 2 pi. These are angles that we already know the sine of. Okay. Now, we just go and we take the sines. So the sine of 0 is 0 because that's the y value. The sine of pi over 2 is 1. We take the y value. So here's 1. Sine of pi over 2 is 1. The sine of pi is 0. We're taking the y value. The sine of 3 pi over 2 is negative 1. We take the y value. And finally, the sine of 2 pi, which brings us all the way around the circle, okay, is 0. And now we just connect. And this is a curve as we get closer to the top, right? That curve flattens. So it should flatten here. This should be the peak. It doesn't look perfect. But it should not look like this. That would be incorrect. I should never see that on anybody's paper. Okay. So we get the sine by looking at the y values of the angle in the unit circle. Okay, we're going to get the cosine the same way, except we're going to look at the x values. So we're going to do the graph again. We're going to use the same exact angles because we know the cosines of those angles. So we're going to look at 0. We're going to look at pi over 2. We're going to look at pi. We're going to look at 3 pi over 2. And we're going to look at 2 pi. Okay. Now at 0, we're looking at the x value. So the cosine of 0 is 1. The cosine of pi over 2 is 0. The cosine of pi is negative 1. The cosine of 3 pi over 2 is 0. And the cosine of 2 pi is back at 1 again. Okay, so what does this mean? These are maximums. They should look like maximums. So in other words, it should not look like a V. Okay, this is a maximum. So it comes around, it's flat at the top. Then we flat when we get down here to the minimum. And then we flatten again. Okay, and this is y equals cosine of x. Again, we take these 4 points and we base it. We use the x and the y values in order to get the sine and the cosine. Okay, and we could go on. We could go on in this direction forever because we could go around the circle an infinite number of times. We can also go on in the other direction because we could go around the circle clockwise. And remember, if it's clockwise, then our angles are negative because we switch directions. So we just put a negative sign in front. Okay, so let's take a look at these graphs where it's easy to see what's going on. Okay, so this is the sine graph. So you could see the sine graph here. Okay. So at pi over 2, it's 1. At pi, it's 0. At 3 pi over 2, it's negative 1. At 2 pi, it's 0. And you can see it keeps going and going and going in both directions. Okay, we could keep going. Okay, so this would be the sine. Let's take a look at the cosine. Okay, so here we have the cosine. At 0, it's 1. At pi over 2, it's 0. At pi, it's negative 1. 3 pi over 2, it's back to 0 again. And at 2 pi, it's 1. And we can keep going and going and going in both directions. Okay. So how do we get the graph of tangent? So the graph of tangent is sine over cosine. So let's put the sine graph back on there for a second. Okay. And notice this is a translation. And we're going to talk about this in a few minutes after we look at the graphs. This is a translation. This is a shift by pi over 2. Okay, we're taking a graph and we're moving it pi over 2 to the right or to the left, which makes sense. We said in the last lecture, okay, let's go back a few pages. We said it in the last lecture that the sine of an angle is equal to the cosine of its complement because the opposite and the adjacent switch in a right triangle. So the sine of an angle is equal to the cosine of its complement. Okay, if this is O over H, then at 90 minus theta, okay, at cosine of 90 minus theta, the opposite, the adjacent is the same as the opposite for this angle. So they wind up being the same, okay? So if the sine of an angle is equal to the cosine of its complement, what we're saying is that when we take the sine, it's the same as taking the cosine of the angle that's 90 degrees later. So you can see that this is a shift by pi over 2. Pi over 2 is 90 degrees, right? So pi over 2, if we take the cosine graph and we move it pi over 2 to the right, we get the sine graph, okay? So this is just a shift. We just translated it, okay? And then you get the same graph. Okay, the tangent. Well, the tangent is the sine over the cosine. So the sine graph is the one in red, and the cosine is the one in blue, okay? The sine over the cosine. Well, here the sine of 0 is 0, and the cosine of 0 is 1. So the tangent is going to be 0. Here, if we look at pi over 4, which we'll have to do, the sine and the cosine are the same. So when you take a number and you divide it by itself, you get 1. So the tangent of pi over 4 is 1. Here they switch. The sine is 1 and the cosine is 0. So we get something undefined. And we know from rational expressions, okay, and reciprocal functions, that when your denominator is 0, you get an asymptote. So we're going to have an asymptote at pi over 2, okay? And notice that that happens multiple times. We're going to have an asymptote whenever cosine is equal to 0. So we're going to have an asymptote at pi over 2. We're going to have an asymptote at 3 pi over 2. If we keep going past 2 pi, we're going to have an asymptote at 5 pi over 2. This is because tangent is sine over cosine. And whenever we have a cosine that's equal to 0, our tangent is going to be undefined, okay? So we will have asymptotes there. Let's write that down. This is what's going to help us distinguish between different graphs, okay? So tangent of theta is equal to sine of theta over cosine of theta. So when cosine of theta equals 0, we will have an asymptote at tangent of theta. Okay, so let's take a look at the graph. This is the graph. Now, imagine dashed lines, okay? So I'll take out the other graphs in a second, but you can see that tangent of theta is 0 when sine of theta is 0, because 0 over anything is 0. So remember, the red graph is sine. So we're going to go to wherever sine is 0. Sine is 0 here. The green graph is 0. Sine is 0 over here. Notice the tangent is 0. Sine of 0 is sine of 2 pi is 0. So the tangent of 2 pi is 0. Okay. When cosine is 0, that's where the blue graph. So where cosine is 0, we have an asymptote. Cosine is 0, we have an asymptote. Cosine is 0, we have an asymptote. Okay, so this is what's going to help us identify. Let's look at tangent all by itself now. This is what's going to help us identify tangent. Okay, so when you're asked to do this, you're going to get a graph and it's going to say, what is this a graph of? And you're going to have to identify the graph, okay, and explain why. So one of the reasons that we know, one of the ways that we know that this is tangent is because we have asymptotes wherever the cosine is 0. The tangent of 0, okay, the tangent is 0 whenever the sine is 0. So when we look at this, we have asymptotes. So that's one thing that tells us that we have tangent as opposed to, let's say, sine or cosine. And our asymptotes are at pi intervals of pi at pi over 2. So we have pi over 2. Then we have 3 pi over 2. These are all asymptotes, okay? And one other thing that's going to be helpful is that this graph rises as we go from left to right, okay? As we go from left to right, our y values increase. So let's write that down as well, okay? So at cosine of theta equals 0, we have asymptotes. When sine of theta equals 0, tangent of theta equals 0. Equals 0, not theta. Okay. And the tangent graph rises from left to right. This is going to be helpful when we look at other graphs. Okay. Let's look at a different graph. Let's look at cosecant. Here's cosecant of x. Looks crazy, right? It looks almost like we took a graph and turned it inside out. Well, why is this cosecant? First of all, if you look, we have asymptotes here. We have, sorry about that. We have asymptotes at 0. We have asymptotes at pi. We have asymptotes at 2 pi. Why do we have asymptotes? Well, cosecant is the reciprocal of sine, right? It's 1 over sine. And once again, we know from our reciprocal functions that when the denominator is 0, we have, it's undefined, which means we have asymptotes, okay? So that's one thing that we know. Also notice there is nothing between 0 and 1, between -1 and 1. There are no values between -1 and 1, okay? Which also makes sense. The sine, the values are between -1 and 1, okay? But then we flip it. We take it and we turn it upside down. So it makes sense. If sine is 1/2, cosine is going to be 2 over 1. If sine is 1/3, cosine is going to be 3 over 1, okay? Our numbers are always something that's less than 1, so when we take the reciprocal, we're always going to get something greater than 1. So it makes sense, okay? There's also something else that can distinguish the cosecant graph from every other graph. If you take the minimums and the maximums and you connect them, you get the sine graph. So let's write that down. Cosecant of theta is 1 over sine theta. This means when sine theta is equal to 0, we're going to have asymptotes. There are no values between -1 and 1. This is because the reciprocal of a number that's less than 1, right? Sine is always less than 1. Is always going to be a number greater than 1. And the last thing is when we connect the minimums and maximums of cosecant of theta, we get the graph of sine of theta. These are things that distinguish it from all other trig graphs, okay? From all the other graphs of trigonometric functions. So both tangent and cosecant have asymptotes, okay? But where are their asymptotes? The asymptotes at tangent are when cosine of theta equals 0. The asymptotes for cosecant are when the sine of theta equals 0. What's the other difference between these two? Tangent doesn't have minimums or maximums, but cosecant does, okay? So if you want to distinguish between these two graphs and you want to say, hey, I know that's cosecant, you're going to say it's cosecant because we have asymptotes when sine is 0, and we have minimums and maximums. These are two things that distinguish it. You can add in, these are other aspects of the graph that make it different than others. There are no numbers between 1 and -1. Okay, when we connect the minimums and the maximums, we get the graph of sine. Let's look at the graph of secant. And we'll see what distinguishes that. Okay, the graph of secant, not surprisingly, looks very much like the graph of cosecant, right? That makes perfect sense. Sine and cosine look practically the same. So why wouldn't secant and cosecant look exactly the same? So what's the difference? We still have asymptotes, okay? But where are our asymptotes? Well, secant is 1 over cosine. So our asymptotes are going to be wherever cosine is equal to 0, okay? So that's its way to distinguish between cosecant and secant. Once again, there are no values between -1 and 1. Okay, again, that makes sense. Cosine is a number that's less than 1, so secant would be a number that's greater than 1. And if we connect the minimums and the maximums of secant, we get the cosine graph. So these are things that help you distinguish the graphs from one another, okay? So let's write that down. So this is for secant. Secant of theta is 1 over cosine of theta. What are some of its distinguishing characteristics? When the cosine of theta is equal to 0, we're going to have asymptotes. Now this does not distinguish it from the tangent, right? Because this is true for tangent as well. So if we ask you, which graph is this? And you say, well, I know it's the secant graph because it has asymptotes when cosine of theta is equal to 0. Well, that doesn't tell me why it's not the tangent graph. So usually you need a couple of things to distinguish. So if you said, well, when we connect the minimums and the maximums of the graph, we're going to get the graph of cosine. That's something that distinguishes it from all other graphs. It doesn't have that in common with any other graph. So you need to make sure that you put in enough characteristics to say, okay, well, this is what makes this graph different from all others. So sometimes you can do just one. Like, for example, here, this makes this cosecant graph different from all of the others, okay? If we just said that there are no values between -1 and 1, how do we know whether it's the cosecant or the secant? Okay, we need more than that. So once again, there are no values between -1 and 1. I'm not going to explain that again. It's for the same reason that there are no values between -1 and 1 for the cosecant graph. And when we connect the minimums and the maximums, of secant of theta, we get the graph of cosine of theta. So these are different ways that we could distinguish between these three graphs, okay? Secant and cosecant and tangent all have asymptotes. Sine and cosine don't. So when you say that it doesn't have an asymptote, we know that we're dealing with either a sine or a cosine graph. How do we know which? Well, maybe you have to say the sine of 0 is 0 and the cosine of 0 is 1, and that's how you can distinguish between those two graphs, okay? Let's take a look at the cotangent graph. So the cotangent graph, not surprisingly, is very similar to the tangent graph, okay? Saying it has asymptotes doesn't distinguish it from the other trig functions, right? It says it's not the sine or the cosine graph, but it doesn't tell us that it's not tangent, cosecant, or secant. So we need more. There are no minimums and maximums, right? There are asymptotes. Where are there asymptotes? Well, cotangent is cosine over sine. So these asymptotes are when sine is 0, whereas for tangent, the asymptotes were when cosine was equal to 0. This also falls from left to right. That's how we distinguish it from tangent. So it has no minimums and maximums. It has asymptotes, but its asymptotes are when sine is equal to 0 and it falls from left to right. So these are distinguishing characteristics, things that make cotangent cotangent, okay? So let's write that down. And then we'll compare all of the graphs. So cotangent of theta is cosine of theta over sine of theta. So when sine of theta equals 0, we will have asymptotes. Notice that's not enough to say that it's cotangent, right? Because we can see up here that cosecant also has this characteristics. When sine of theta equals 0, we're going to have asymptotes, okay? This has no minimums or maximums. And it falls from left to right. We can even add what the other piece that we have under tangent, that when cosine of theta equals 0, tangent of theta equals 0. So let's add up here that this has no minimums and maximums. Okay. So how do we distinguish between the graphs? We're looking for asymptotes. If it has asymptotes, it's got to be one of these four. Okay. We're looking at where those asymptotes are located. If the asymptotes are located when cosine is 0, then it's either going to be tangent or secant. Now, just to distinguish between tangent or secant, we could look, do they have minimums or do they have minimums or maximums? If they do, then it's secant, right? If they don't, then it's tangent. So that's how you can distinguish between them. So you look at asymptotes. You look at where the asymptotes are located. Now you can also look at, how do we distinguish between cosecant and secant? Well, cosecant, when you connect the minimums and maximums, you get sine of theta. Secant, when you connect the minimums and the maximums, you get cosine of theta. What's something else that we could see? Well, we have asymptotes when cosine of theta equals 0. What's another distinction between tangent and secant? Secant, there are no values between -1 and 1. Tangent, there are. How do we distinguish between cosecant and cotangent? Same thing. There are no values between -1 and 1 at cosecant. How do we distinguish between cosecant and secant? Well, they both have asymptotes. They both have no values between -1 and 1. But we could look at what the graph looks like when we connect the minimums and the maximums. Now, sine and cosine, they don't have asymptotes. They're the only graphs that we've looked at so far that don't have asymptotes. So now we just need to be able to distinguish between sine and cosine. Okay. Well, again, you can look at the value at 0. The sine of 0 is 0. The cosine of 0 is 1. And that's how you can distinguish between them. So if we give you, you're going to see this. There's no way I could hide this from you. But if I give you this graph and I say, what is this a graph of? You're going to say, okay, it has asymptotes. So it's either tangent, cosecant, secant, or cotangent. Well, when I connect the minimums and the maximums, I get sine. So it's got to be cosecant. That's one thing that you could do. You could say, well, there are no values between -1 and 1. So now we know it has to be secant or cosecant. And it has asymptotes at 0 and pi. Well, that's where sine is 0. So this has got to be cosecant. Okay? So you're looking at the different aspects of the graph and you're saying, okay, well, now it can only be cosecant or secant. Well, how do I distinguish between cosecant and secant? Let's say, for example, I give you this graph. Well, there are no minimums and maximums. That means automatically the only possibilities are tangent and cotangent. Well, this is rising from left to right. Rising from left to right means it's got to be tangent. Okay, so these are what we're looking for. We're saying, okay, here's a graph. How do we know it's that graph? Here's another graph. Well, there are no minimums and maximums. Again, it must be either tangent or cotangent. Those are the only graphs that have no minimums or maximums. Okay, well, which one is it? It's got to be cotangent because it falls from left to right. Or if you said, okay, it's got to be tangent or cotangent, my asymptotes are wherever sine is equal to 0. That's another reason it's cotangent. Okay, tangent, the asymptotes are where cosine is equal to 0. What's this one? Well, this one has to be secant. How do I know it has to be secant? There are no values between -1 and 1. Automatically makes it either cosecant or secant. My asymptotes are where cosine is equal to 0. Okay, cosine is equal to 0 at pi over 2, at 3 pi over 2. It's got to be secant then. Okay, so you're distinguishing between these graphs. You're taking different characteristics and you're saying, okay, well, it's got to be this or this. Well, how do I distinguish? You could say, well, it's got to be secant or cosecant because it's got minimums and maximums and there are no values between -1 and 1. Which one is it? Well, when I connect the minimums and the maximums, I get cosine. So it's got to be secant. Okay, so those are the different ways. Now, if we looked at this graph instead, you're going to say, okay, well, there are values between -1 and 1 and minimums and maximums. So, or there are no asymptotes. So it's got to be sine or cosine. Which one is it? Well, at 0 radians, we have 1. What is that true for? That's true for cosine. Okay. So that's how you would identify different graphs. Now, this is for the graphs of the trigonometric functions and their reciprocals. What about the graphs of the inverses? Okay, so for the inverse functions, for inverses, the x and the y switch. Right? It's a reflection in x equals y. So the x and the y switch, which means that, for example, if we graph sine, right? We have x and we have the sine of x. So we know that at x, at 0, the sine of 0 is 0. At pi over 2, the sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is -1. And the sine of 2 pi is 0. Now let's do sine inverse. The x and the y switch. So at 0, the sine inverse is 0. At 1, the sine inverse is pi over 2. At at 0, the sine inverse is pi. -1, the sine inverse is 3 pi over 2. And at 0, the sine inverse is 2 pi. The x and the y switch. Okay, so let's take a look at that graph. So let's go to the sine graph. Okay, sine graph. what we're doing is we're taking this graph and we're reflecting it in the line y equals x, okay? But if you look at the sine of x, what you're going to notice is this is not one-to-one. In order for the function to be one-to-one, you have to, it has to pass the horizontal line test, right? Well, we can do that because this graph is repetitive, okay? So we could essentially erase all of the things that repeat. So we have y values that repeat over and over again. So what we're going to do is we're going to take only a piece of sine, and that's going to be enough because, like we said, if we know the sine of 30 degrees, we know the sine of 150 degrees. We know the sine of 210 degrees. We know the sine of 330 degrees. So we don't have to take the inverse of every single x value. We could take the inverse just of some. So if we take this piece starting at negative pi over 2 and we travel up, we're getting all of these y values. We're going up to pi over 2. And then once we pass pi over 2, it repeats. So we don't need that. We're going to take that out. And we're only going to take from negative pi over 2 to pi over 2. And we're going to reflect that. From negative pi over 2 to pi over 2, it's a one-to-one function. It passes both the horizontal and the vertical line test. So we're looking at this. We're reflecting this piece. Now notice, these graphs are easy to recognize because the x and the y values switch, so the labeling of the axes switches, okay? And again, it only goes from negative pi over 2 to pi over 2. That's the range. So the domain is now negative 1 to 1, but the range of the graph is just negative pi over 2 to pi over 2. Okay, and the reason why we do that is, again, because all of these values would be repetitive. You don't have to repeat them all, okay? And you want it to be a function. So we erase all of that extra stuff, and we say that the range for sine inverse of x is negative pi over 2 to pi over 2. Okay, and the axes are switched. So this is how you know that it's an inverse graph. As soon as the axes are switched, you know it's an inverse, and then you're looking at the range. Because the range, if we take cosine, let's take a look at cosine. So let's first look at the cosine graph. And you're going to see the same problem with the cosine graph, right? It's not one-to-one. So this means that once again, we have to delete part of the function. So we want to make sure that we get all of the y values from 1 to negative 1, okay? But we don't repeat any. So we can't go from negative pi over 2 to pi over 2. That's going to fail the horizontal line test. And it means we get all of the positive y values, but none of the negative y values. So the range is different. What we're going to do is we're going to go from 0 to pi instead, because then we get all of the y values that go from 1 to negative 1, okay? And we don't have any repeating values. It passes both the vertical and the horizontal line test. So if we look at the cosine inverse, you can see that it goes from 0 to pi, okay? So once again, the axes are switched, but the range is different, okay? And again, that's because if we kept going this way, it would fail the test. It wouldn't be a function anymore. It would fail the vertical line test. And same thing over here. So we go from 0 to pi, okay? So that's how we can distinguish between these two graphs. There are no asymptotes, so so the range for cosine inverse is 0 to pi. I would like to mention also that cosine inverse of x, and this is true for all of the inverse functions, is most commonly referred to as arc cosine. okay? They mean the same thing. Notice axes are switched here. The same thing is true for sine inverse. Because this -1 is such a crazy symbol, we will often say, we will almost always say, that the sine inverse of x is really arc sine. So you will see it referred to as arc sine. Okay. And tangent, you'll see referred to as arc tangent. Now tangent, you're going to have the same problem, right? If you include every value from 0 to pi over 2, it'll fail the horizontal line test. So you're just going to take a piece of it, and it certainly makes sense to take this piece here in the middle, so which goes from negative pi over 2 to pi over 2. So that will be the range here, okay? And you don't have to look at the inverse of the other graphs. We'll only look at these. So it goes from negative pi over 2 to pi over 2. This does have asymptotes, okay? So it has asymptotes at negative pi over 2 and pi over 2. So that's the way that you would distinguish it from the sine inverse, okay, from arc sine. Arc sine only goes from negative pi over 2 to pi over 2, but it doesn't have asymptotes at those values, okay? So let's write that down. The range for tangent inverse of x is also, and here they're asymptotes, so we approach it but we never reach it. It's negative pi over 2 to pi over 2. The tangent inverse of x is referred to as arctan of x. So the axes are switched, which tells you that it's an inverse graph. It's not enough to say the range, because the range wouldn't distinguish between tangent and sine, okay, between arcsine and arctangent, but it has asymptotes. And this is the only inverse function that has asymptotes, okay? So what does this mean? In terms of exact values, okay, the sine of pi over 3, this is 60 degrees. The sine of pi over 3 is square root of 3 over 2. So the arc sine of square root of 3 over 2 is pi over 3. Okay, and it should be noted that the arc sine of the sine of pi over 3 is just pi over 3. Right, the inverse, whenever you take the inverse of the trig function, right, when you compose inverses, because that's what we did a composition of inverses, you just get the input, okay? When you do something like this, you have to keep in mind that your answer has to be within the range, okay? If it's not within the range, then you have to make it within the range, okay? So if we had said, what is the arc sine, what is the arc sine of negative root 3 over 2, we're saying that the sine is negative, you would have to say, well, it's negative 300 degrees. Okay, because this is between negative 90 degrees and 90 degrees. Sorry, it's negative 60 degrees. Let me say that one more time. This is between negative 90 and 90, right? Negative pi over 2 is negative 90 degrees. Pi over 2 is 90 degrees. That means that when you take the arc sine of an angle, you have to make sure that your answer is within this range, okay? So you are looking at the reference angle. Look at the reference angle. use the reference angle to help you figure out it's in the range. You should always be using the reference angle as your answer, okay? So your answer here and you're going to become, again, you're going to become a lot more familiar with radians when we start doing equations. I haven't spent a lot of time on radians and you're becoming familiar with it. When we do equations, which will be very soon, we will become very familiar with the reference angles. Okay, the last thing I want to talk about in this lesson is transformations of trig functions, specifically just sine and cosine. Okay, so let's take a look at sine and cosine for a second. And as part of this lecture, as part of the board notes, I'm going to include all of these graphs because I know that otherwise they won't be included on the board notes. So let's look at sine. Okay, here's the sine graph. Now it turns out that you can't form a perfect sine wave, okay? It doesn't occur naturally. It's man-made. We create it. If you were to take out a dollar bill right now and you looked at the white webs that are on the dollar bill, those white webs are perfect sine curves. Something else that's a perfect sine curve is middle C. If you play middle C on the piano, that is a perfect sine curve. So these are waves. We have waves all over the world, right? We have ocean waves, we have microwaves, we have radio waves, all different kinds of waves. We have sound waves. So when we transform a trigonometric graph like sine or cosine, it is exactly the same as when we change sounds. The height of the graph is equivalent to the loudness of the sound. Is it a very loud sound or is it a very soft sound? Okay, so a loud sound changes what we call the amplitude. It is a vertical stretch or a vertical shrink. Okay, vertical stretch or vertical shrink. So how do we do a vertical stretch or a vertical shrink? We multiply. So let's say that we multiplied it by 2. We just vertically stretched this graph. If we multiply it by 3, we vertically stretch the graph even more. If we multiply it by 0.5, well, then we vertically shrunk the graph, right? This is lower. This height is called the amplitude, and I'll write this down. Okay, horizontally shrinking and stretching. Well, if we horizontally shrink and stretch, we change the frequency of the sound. So the frequency is what the pitch is. If it's a very high-pitched sound, like, this is a very high-pitched sound, or a very low-pitched sound, like, this is a very low-pitched sound, that's a horizontal stretch or shrink. So when we horizontally shrink it, we're affecting just the x values, right? So it would be as if we did sine of 2x. Well, our waves are shrinking, right? We finish a wave much more quickly. So for the red graph, for sine of x, it takes us 2 pi to get a full wave. Whereas here, it just takes us pi to get a full wave. If we did sine of 3x, we would finish it even faster. And if we did the sine of 8x, well, now it's even faster, okay? And the frequency, again, we're going to write all of this down, is the number of waves that fit between 0 and 2 pi. So sine of 8x says we can fit 8 waves between 0 and 2 pi. Here's 1, here's 2, 3, 4, 5, 6, 7, and finally 8. Okay, so this tells us we could fit 8 waves. We can also figure out how long one wave is, because if we're fitting 8 waves between 0 and 2 pi, then if we take 2 pi and we divide by 8, that tells us how long one wave is. So 2 pi divided by 8 simplifies to pi over 4. So that tells us the length of one wave. If we have sine of 2x, well, that's saying we could fit 2 waves between 0 and 2 pi. So if we take 2 pi and we divide by 2, that gives us the length of one wave. So one wave is pi. That distance is called the period. Now we could also, in addition to changing the frequency and the amplitude, okay, in addition to vertically stretching, vertically shrinking, or horizontally stretching and horizontally shrinking, we can also change the location, right? Because we can change the pitch, we could change the volume, the loudness of the sound, but we could change the location. I could sit over here and right in front of my computer and teach you, or I could walk to the other side of the room and that changes the location, okay? So I might not be changing the volume or the pitch there, but I am changing the location, okay? If you can, I don't know if you can do this when you play a tape, but some of you who are into music or you're recording, certainly when you record, like when I record this tape at the end, if I want to edit it, I can see the sound waves and I could see how much my volume changes and how much my frequency changes, okay? Which will tell me if the wave looks exactly the same throughout, it means I'm very monotonous. I'm trying not to do that. You want to change your pitch and your frequency, okay? So if we want to change the location of the wave, I changed the location. I didn't change the amplitude, okay? I didn't change anything, just the location, okay? Or I can move the wave to the left or to the right. And here we move it by pi, right? By pi or pi over 2, we do it in terms of pi because our x-axis is in terms of pi. So I can move it to the left or to the right, or I can move it up or down, okay? So this is how we change our waves. We vertically stretch them, or shrink them, we horizontally stretch or shrink, or we move them, okay? So let's put it all together. When we change the amplitude, we call it A. A is the amplitude, okay? Then we have sine of B. B is the frequency. Then we have our sliding, okay? I'm going to use minus. I think typically you're going to see H and K. It's usually H and K. So the A is going to change. We're going to add sliders to each of these, okay? Sliders meaning you're going to be able to change it. So let's just take the, let's say that we move it -10 to 10 is fine. Let's do this one first, okay? The K is what moves it up or down. So this, you can see it. I probably should have done it last. -10 to 10. You can see it moving up or down, right? This moves it left or right. So let's move this back to 0. Let's change our this one. Let's do this from -2 pi to 2 pi. And we'll make the step pi over 4. So let's just see what happens to this as we move the wave. Why is this doing up or down? What did I do? Oh, I know what I did. Sorry. I put the parentheses in the wrong place. Okay, now I got it. Okay, so here we're moving it left or right. Now you can't see it. I don't know why this one isn't working. Okay, we're moving it left or right. Let's move this back to 0. Sorry about that. Okay, now we got it. So this is moving it left or right, right? The H, it moves it to the left or to the right, okay? Whereas when we move the K, we moved it up and we moved it down, okay? Goes up and down. The H is what is moving it left and right. So let's put these back at 0. Now you can see the B. Okay, the B increases the frequency or decreases the frequency. So it increases when it gets, when our B gets very large, and it decreases when our B gets really small. Okay, this is a horizontal shrink and stretch. Let's change this back to 1. Okay, and now let's do the A. So the A is going to make it stretch, vertically stretch it, or vertically shrink it. When the A gets really large, you can see that the maximums get very large, okay? And when the A gets small, okay, then it's getting very small. So this should go from 0 to 10. Okay, because I don't want it to reflect it. So it gets really large, and then as the A gets smaller, the height gets smaller and smaller, okay? Okay, let's put them on all together, and you could see how much graphs can change, okay? So this is just an example of how much your graph can change. Okay, so let's write down everything that we said. Okay, I think we'll be able to make it. Transforming, and everything that we say for sine is true for cosine. So it would look like this: A times the sine of B, and then you have x minus h plus k. Okay, so h comma k is the translation. A is a vertical stretch or shrink. A is equal to the amplitude. Okay, if you work in music, whenever you want to make a sound louder, you use an amplifier. Okay, so A is equal to the amplitude. B is a vertical stretch or shrink. I said vertical, I mean horizontal. B equals the frequency. And this is the number of waves that fit between 0 and 2 pi. Okay, now we talk about the number of waves that fit between 0 and 2 pi, okay? But then we also talked about the length of the wave. So the wavelength, or the period, is the length of one wave which is equal to 2 pi over the frequency. So this is not in the equation, right? It's not in the equation, but it's saying if you have 8 waves that fit between 0 and 2 pi, then one wave is just 2 pi divided by 8. Now the amplitude is defined as the distance from the midline, and I'll just tell you what that is in a second, to either the min or the max, to either the minimum or the maximum. I'm going to say to the maximum. So the midline is that y equals k. Okay, so what does the midline mean? Let's take a graph of sine, and let's just mark this off. So this is 1. This will be -1. Here's our pi over 2. Here's our pi, our 3 pi over 2, and our 2 pi. Here's our graph. So we're just going to mark off the midline and the amplitude. Okay, so the midline is literally the line in the middle. So if you translate it up, which I'll show you on the other graph, if you translate it up, then the midline is at y equals 1. If you translate it down by 1, the midline will be at y equals -1. The amplitude is the distance from here to here. Okay, it's the distance from that midline. So if we go back to this graph, the midline here is at 0. Let's say that we change this to sine of x plus 2. If you notice, now our midline is at y equals 2. That's the very center. That's what goes through the center of the graph. Okay, so the midline is at y equals 2 here. Okay, so let's just take a couple of examples and identify. Let's say that if we had y equals 2 sine of 4x, okay? The amplitude here is 2. The frequency is equal to 4, and the period, which is what you would usually identify, is 2 pi divided by 4. If we have y is equal to 1/3 cosine 6x minus pi over 2 plus 8. Well, our amplitude is 1/3. Our period, our frequency is 6. You should always simplify. Your period is 2 pi over 6. or pi over 3. This is telling you the length of the wave. From beginning to end, it's pi over 3. And then your translation, well, you're going pi over 2 to the right, and you're going 8 up. If we have, notice that cosine makes no difference. If we have y equals 7 sine of 2 x plus pi over 6 minus 4, this is saying the amplitude is 7, the frequency is 2. I'll put parentheses around these as well because I did that originally. The period is 2 pi over 2, or pi. And the translation, well, you're going pi over 6 to the left and 4 down. And if you're told instead the amplitude is 1/2, the period is 2 pi over 7, and no translation, we won't do any translation, then if we want the graph, we need b, right? So 2 pi over b is equal to the period, which is 2 pi over 7. So if we solve, we get that b is equal to 7. You can cross multiply. So here it's very easy to see. You have 2 pi times 7 is equal to 2 pi times b. So if you divide both sides by 2 pi, the 2 pi cancels. Okay, you can cross multiply. So what does this mean our graph is? I would have to tell you which function to use. This is cosine 1/2 cosine of 7x is equal to y. Okay, and we could look at this a little bit more in the next lecture, but I'm going to stop here because this has been a very long lecture up until this point, and we've covered a lot of material. And we'll do a little bit more of this in the next lecture and how to graph. So that's it for today. It may take me a second to stop the recording, so stop listening now.